Hello, everybody. Welcome back. All right, let's let the Discord know I am live. Welcome back, everybody. We are here and we are ready to jump back into learning Python, more specifically data structures and algorithms in Python. It's been a grind so far, guys. Okay, I think we're good. I think our connection's kind of all over the place, but I think we're okay. Okay, cool. All right. Awesome. Well, welcome back, everybody. I hope you're having a wonderful day so far. Happy weekend. We made it. We made it to Friday. Tomorrow's Saturday. We made it to the weekend. Hope everyone's having a great December so far. And yeah, thank you so much for joining me today. So we are jumping back into data structures and algorithms in Python here. Um, so we had some examples of algorithms. Okay, hold on. Oop. Are we okay here with the stream? Jeremy, welcome. How's the stream? It's kind of giving me a message here saying like an error. Is everything good with the stream? Let me check the channel here. Seems to be okay on my end. The stream. Jeremy, welcome. All right, seems to be okay. All right, yes, Friday night grinding, right? Instead of going out, we're not going out. We're not doing anything crazy. We're reading out of a textbook here, right? So, all right, thank you for joining me, Jeremy. I appreciate you coming in. All right, so last time we talked about we introduced so we obviously went over the seven main functions covered in this book, and then we started to dive into asymptotic analysis, where we talked about growth rates. Um, right? And we were given we were introduced to big O, big omega, and big theta analysis. Um, and so I kind of watched some videos last night regarding this just to help kind of solidify the topics even further. And it really helped actually. Maybe we should watch a video here on the channel. I'm not sure how that would work. I'm not sure if YouTube would really like that with a live stream, but um, I'm not sure. But anyways, it really helped to kind of enlighten the aspects of. Let's go to the show me the graph for the seven functions um, in DSA. Okay, we're gonna let's get the graph here. Come on now. Whatever, I'll just look it up on Safari. Oh well. This guy here. So we have this graph here. So we were given these 1, 2, 3, 4, 5, 6, 7 functions. These were our seven functions. Obviously, they should be familiar from our notes. We have worse increasing to, best, most efficient. Um, and so I watched some videos last night to help kind of solidify these concepts, and it was really helpful because he mentioned that these are bounds, and I wasn't fully understanding what the word bounds meant. Like, I didn't, like, I was kind of dodging over the fact of what a bound actually was. And so by upper bound, it just means like our function lies somewhere on this graph, right? And the upper bound is just the most recent function that has the most similar slope pattern, or or just a similar function in general speaking, right? So um, I wish I had like a paint. Do you guys know what like a paint on Mac would be? Like so I can draw like a really like an easy. Is it in the App Store or something? Let's see here. Paint. Okay, let's see. Let's get this paint. Let's get this whiteboard app here. Open this guy. Let's see here. Okay, so what happened? Okay, let me go back. So yeah, we have our graph here, right? And let's say we just have our function f of n, right? We have a function f of n. Oh my gosh, brutal, right? This is our function, right? We want to know like the bounds are just like the closest, relation. And from what I'm understanding, is the closest, upper and lower instance of where these, g of n would lie in relation with the constant c, so with some constant c. So, which is interesting to think about. So if we had some function n here, right, we have like a linear, right? We have our quadratic, or right? We have a log linear, stuff like that. We have this guy. So really, this one right here would be the bound associated, and this one would be the other bound. Now, theta, on the other hand, I didn't get to that part of the video. I kind of fell asleep last night to help further solidify that concept. But it kind of really helped to um, understand, rather, that my function just lies somewhere on this graph in itself. And I'm trying to determine the time, most similar to its upper limit or its lower limit, and then in the case of theta, kind of the average between the two, that where it lies. Um, so, which is what I need to further understand. But hello, everybody. I appreciate you joining me tonight. So we got quite a few people in here already, and that's really exciting. We got Jeremy, Peyton Gardner. Good evening. How are you doing? I appreciate you coming in here and leaving a message, and doing great. It's Friday, made it here past my 9 to 5 during the week, and I'm a chemist, and I was starting to get my product ready. I'm going to start building it this next week. Just getting everything prepped, all my solutions, testing materials. I had a lot of preliminary testing I had to do, and then data analysis on that testing, and so there's just a lot of work leading up to this point, because it's just this very large product that I kind of specialize in for my team. And yeah, it's pretty it's kind of a challenge and a big old task, but it's a good one. It keeps my brain going at work, at least. So the bound. Okay, so let's go ahead and continue on here. So we had a quadratic time algorithm we talked about, or last time we talked about the prefix averages. No, the yeah. So we talked about the harmonic number last time, which was log n times, right? And then we were introduced to this prefix average function. So, and I think this is where we're going to start out first today. So we've got about 10 more pages left in chapter 3, and then we can dive into the actual practice problems and solidify these concepts even further. So just bear with me, guys, while we get a couple more learning segments in here. So The prefix averages. The next problem we consider is computing what are known as prefix averages of a sequence of numbers. Namely, given a sequence S, right, consisting of numbers, we want to compute a sequence A, so a new sequence, such that A at some index value of J, at some point J in the sequence, is the average of elements of S to 0 all the way through S to that index value of J. Okay, for J starts at index 0 and it goes all the way up until n minus 1. Okay, prefix averages. Computing prefix averages has many applications in economics and statistics. For example, given the by-year returns of a mutual fund ordered from recent to past, an investor will typically want to see the fund's average annual returns for the most recent year, the most recent 3 years, or the most recent 5 years, and so on. Likewise, given a stream of daily web usage logs, a website manager may wish to track average usage trends over various time periods. We analyzed 3 different implementations that solve this problem, but with rather different running times. Okay. So this is an example of a quadratic time algorithm here. Okay. Our first algorithm for computing prefix averages, named prefix average 1, is shown in code fragment 3.2. Yeah, we talked about this one last time. This is familiar, but I'll just go over this really quickly. So this is just a function where we take in a sequence S. We have a value of n, which is just the length of the sequence. So this will be an integer. We set our A sequence, so our new sequence, to a list of zeros multiplied by the value of n. So we just get a sequence the same size as length S, but just full of zeros. And then for J, so we're going to establish this index in the range of our length, right? So we're going to try to establish an index saving. We have a counter, and then we also have an index going on as well. So the I is what's happened interesting here. This is kind of what throws me. So I know that because we have a for loop and another nested for loop, we're looking at a quadratic time algorithm. But what exactly does I save in this problem? Let's try to figure that out. So we know that J saves the index value of the range n, right? And then for I in the range of J, the index value plus 1. So this just saves the next number. No, the range of J plus 1. So this creates a new sequence, or a new range. Yeah, this part is what's really throwing me. So then we add to our total sequence from our original sequence at index I. Okay, because you can't divide by 0 here, right? So you have to already divide by 1 for just an average of 1 value, or J. So J is the amount, J is our sequence length, or no, our index values. Yeah, this is really interesting. It's pretty, I'm sure with practice I'll get it, but it's definitely new seeing these nested for loops together, and then doing 2 range functions, and then it's pretty confusing, to be honest. Be lying if I said it wasn't. Santosh Tech, thanks for joining me. I appreciate you coming in and leaving a comment. That's really kind of you. Jake, hello. Appreciate you coming in. Distracted Funny, hey, how you doing? I appreciate you coming in. Just got off work. Me too. I got off work about an hour and a half ago, 2 hours ago. But just hanging out for a bit, and then got on the stream here. But appreciate you guys joining me today. We're just continuing on here. So let's go ahead and analyze this algorithm step by step. Okay, so we know that the statement n length s executes a constant time as described at the beginning of section 3.3. The statement A with a list 0 multiplied by n causes the creation of an initialization of a Python list, yes, right here, with this syntax, with the length n. So it's going to be equal to our original length of s. And with all entries equal to 0, right? This uses a constant number of primitive operations per element and thus runs in O of n time. So we multiply by the value of n with a constant, c times n, which is our function. F of n equals c times n, right? There are two nested for loops, which are controlled respectively by counters j and I. The body of the outer loop, controlled by the counter j, is executed n times, for j to 0 all the way to n minus 1, right? Because we have a range of n from all the way from j to 0 to all the way to n minus 1, right? Therefore, statements total equals 0 and array A at index j equals total divided by j plus 1 are executed n times. So this is just finding that average of... Interesting. This implies that these two statements are executed n times. This implies that these two statements plus the management of the counter j in the range contribute a number of primitive operations proportional to n. That is O of n time. The body of the inner loop, which is controlled by the counter I, is executed j plus 1 times, depending on the current value of the outer counter loop counter j. Thus, statement total plus equals the sequence s at index I in the inner loop is executed 1 plus 2 plus 3 all the way n times. Recalling proposition 3.3, we know that 1 plus 2 plus 3 all the way to n equals to that same function we saw earlier, n times n plus 1 divided by 2, just the summation function of n, which implies that the statement of the inner loop contributes in O of n squared time. A similar argument can be done for the primitive operations associated with maintaining counter I, which also takes O of n squared time. The running time of the implementation prefix is given by the sum of three terms. The first and the second terms are O of n, the third term is O of n squared, and the third term is O of n squared. By simple application of proposition 3.9, running time of prefix average 1 is O of n squared. Schweppes, appreciate you coming in to chat. Bro, your notification is a motivation for me. When it pops up, I get back to work. Awesome, I appreciate that. I hope that helps. My hair's kind of crazy tonight. It's kind of flat, to be honest. Oh, oh well. I'm doing DSA on C++ right now. Awesome, that's really cool, Swebs. I appreciate you letting me know that. Same, just finishing up my notes from my software engineering final. Awesome, Peyton. How's that going? Avinash says, I'm learning Python and full stack web development through the Odin project and full stack open. That's really cool, man. I have done about half the Odin project, but I kind of shifted back into Python because I realized that I wanted to keep focusing on Python and dive further into these concepts before I moved on. But and I needed to create a quick website for my girlfriend. Yeah, it was fun when I just learning that little bit, that first half. Jeremy says j plus 1 ensures the second loop can actually loop because it won't when j equals 0. So for I in range j plus 1, for j in range n. Okay, so if we have for j in range n, that means j can be 0. So we know that j plus 1 because we can't have range of 0. So we need to have a minimum range of j so we can count the indexes of the values that pass in our sequence here. Because a sequence of numbers that wants to compute a sequence A such that j interesting. Yeah, it's definitely challenging to kind of wrap my head around here. Okay, let's check the chat here. Roland Owner, what's up, dude? Let's learn together. That's awesome. I appreciate you coming in and leaving a comment. I have a Discord below where I have all of my study resources and conglomerated into one space this weekend. I'm going to heavily work on adding in some more, such as some, my solutions to the CS50P course that I did, those data sets. I'm going to make some private videos just for the Discord. Um, I think people could use those to help learn as well. Obviously, just a disclaimer, you don't want to be like copying and things along those lines, but you definitely want to be learning and taking in the information and applying it into your own solutions and things like that. But I definitely think that it could help people, especially beginners, that get stuck in those problems because they can be pretty challenging for a new person, at least for when I did them. Um, cool. So let's continue here. So our second implementation for computing prefix averages. Prefix average 2 is presented in code fragment 3.3. So we have a sequence here and we take the length. We create that new sequence and we say for j in range of n. So we are finding the index value for our sequence length. Or saving the index value. Um, a at that index j is equal to the sum of our sequence um, from position 0 all the way to j plus 1 divided by j plus 1. Interesting. So we use a built-in sum function here rather than creating a counter to sum the entire sequence. This approach is essentially the same high-level algorithm as prefix average _1, but we have replaced the inner for loop by using a single expression, sum. Yeah, we use this sum function instead to compute the partial sum of sequence s at index 0 all the way to s at index j. While the use of that function greatly simplifies the presentation of the algorithm, it is worth asking how it affects the efficiency. Asymptotically, the implementation is no better. Even though while the use of the function greatly simplifies the presentation of the algorithm, it is worth asking how it affects the efficiency. Asymptotically, it's no better. Okay. Even though the expression sum sequence s at position index 0 through j plus 1 seems like a single command, it's a function call, and evaluation of that function takes O of j plus 1 time in this context. Technically, the computation of a slice, we're taking a slice of this sequence, also uses O of j plus 1 time, as it constructs a new list instance for storage. So the running time of prefix average 2 is still dominated by a series of steps that takes time proportionally to 1 plus 2 plus 3 all the way to n, and thus O of n squared. Interesting. All right, One Fit Squad says, what's your overall goal? Are you currently a software engineer or just a guy learning a new skill? Side note, I'm just a guy learning a skill right now. Well, that's awesome to hear. I appreciate you sharing with me and reaching out, and joining the stream. That's really awesome. I'm happy you got fate brought you here because I'm also just a random guy trying to teach myself how to program. I have a bachelor's of science in human biology and minor in chemistry, and I graduated back at the end of 2021 and have been a working professional as a chemist for 3 years now. And I have some instances in my work where I develop, I do a lot of hand calculations, and that's what sparked the interest to maybe want to develop programs to do those calculations for me. And then I started just diving into CS50P and then into some books and created the channel, and here we are. So, um, yeah, we have a couple of projects pushed to the GitHub right now, our task tracker project that we completed. So check that out if you're wanting to have a cool task tracker application on your device. And yeah, and join the Discord if you're also wanting to get access to a conglomerate of all of my study resources. Okay, so we're going to look at a linear time algorithm now. So this is going to be maybe a little bit easier, hopefully. Our final algorithm, prefix averages 3, is given in a code fragment 3.4. Just as with our first two algorithms, we are interested in computing for each j the prefix sum of sequence 0 plus sequence index 0 plus sequence all the way to j, right? Denoted as a total in our code, so that we can then denoted as as total in our code, so we can then compute the averages in this statement here, right? So what it does is so what it does is this function, now I kind of understand what this is doing, I think, is it's iterating over the list j plus 1 times. So at first you're going to get sequence at position 0. That's going to get saved into our list here. Then it's going to do sequence 0, position 0 plus sequence 1, because j will then be 1. So then it's going to save that value, and then it's going to go up one more, all the way to the end of the list, and save all those values in that new sequence. Then it's going to average all those values and return the average. So it's just taking the average, the new average after. So like think of these as like they said earlier, as new years for like a mutual fund. So if this was the start, it had 0, and then the next year it had like a $10 fund price, then it would be 0 and then plus 10, and then it would take the average over those years to compute the 3-year running average, the 5-year running average, the prefix average. That's how those are computed. So I'm getting it now. Interesting. So you guys got to keep working with it. You got to keep reading through. Don't give up. You can have that blank stare but you just keep thinking about it, keep pushing through, and it kind of comes little by little until you can put the pieces together. Okay, so however, there's a key difference that results in much greater efficiency. Okay, so this one's going to be much more efficient, right, because it's in linear time rather than quadratic time. Okay, so this one, we take in a sequence again. We do the same thing. We save the length. We create our new sequence of the same length as sequence S, but this time we but this time we have total here outside the loop, and we say for j in range of n, total plus is equal to that sequence at that index value. And then you just take the average and return. So why does this one work? In our first two algorithms, the prefix sum is computed anew for each value of j. That contributed O of j time for each j, leading to the quadratic behavior. In algorithm prefix average 3, we maintain the current prefix sum dynamically, effectively computing O at index 0 all the way to j as total plus sequence index j, where value total is equal to the sums computed by the previous pass over the loop over j, of the loop over j. There is a single for loop which is controlled by the j counter. The maintenance of that counter by the range iterator contributes an O of n time. The body of the loop is executed n times. Thus, statements total plus is equal to sequence j, index j, and sequence a index j is equal to, are executed n times each. Since each of these statements uses O of n times per iteration, the overall contribution is an O of n time. So I'm trying to think how are they doing this differently? How is this doing the same thing as this function above? So in this one we have a counter outside, but this is inside the loop. Now we have a counter outside of the loop. Okay, let's get caught up on the chat here. Oh, the Discord link is invalid. I am sorry. Let me go ahead and change that. I thought I made it so it would never expire. I'm sorry. Copy. Oh, no, let me. Okay, now let me put this in the update the description of the stream. I'm sorry. Okay. Edit video. Give me one sec. Apologies. Ooh. Okay. Now it should be good. Hello, Vanch. I appreciate you coming in. Let's get caught up on the chat here. One Fitzgerald says, what exactly are you reading? Yeah, we're reading Data Structures and Algorithm in Python. This is a, I believe, a college level textbook for DSA and Python. At least I hope it is, because I'm struggling. But yeah, you can either find this online just by researching it, looking this up online, or I provide just a PDF or file in my Discord for people to access. So what's this doing? So our first two algorithms, prefix sum is computed anew for each value of j, right? Yes, we know that, right? Because we are, for every value of j plus 1, we are creating a new sum at index j, okay? But in this function, what are we doing? That contributed to O of j time leading for each j, leading to the quadratic behavior. In algorithm prefix _3, we maintain the current prefix sum dynamically, effectively computing sequence index 0 plus sequence index 1 all the way up to sequence at index j as total plus sequence j, where total is equal to the sums computed for all the previous passes over the loop j. So instead of so we're getting the index, we're adding total, and then we're just interesting. Okay, so let's actually sorry, stuttering a lot. Let's walk through the loop itself. So for index 0 in range, let's say our range is 5 to keep it easy. So this is 0, 1, 2, 3, and 4 are our values in this range because we start at index 0, right? So j is first 0. So we're going to then say total we're going to add that value of sequence, so it'd be 0 is added to total. So total is still 0. Then we're going to go to the next iteration, index value. So j is now 1, right? Now, and then so you just, rather than creating a new list and slicing and then, or, tracking another integer value with another range function here, they just do the computation all in one function and then just return, and then just like pretty much like our are accessing that one data point inside of this list here. I mean, they were doing it in the previous ones, but this one definitely makes more sense. So let's go on to the next value. So for the next one is j is 2. So we're now at index value 2. So in our sequence, let's say that that is literally 2. So total is now, oh, because they have total set to 0 by default outside of the list. No, because by having total inside of the list equal to 0, I'm trying to figure out at what point does total reset back to 0. Does it not reset back to 0 in this instance? No, it would after every iteration of this one. Whatever. Yeah, so this established in O of n time. The running time of algorithm prefix 3 is given by the sum of, okay, we talked about that one. No, is given by the sum of 4 terms. The first is O of 1, and the 3 remaining are O of n. By a simple application of prop 3 to 9, the running time of prefix average 3 is O of n, which is much better than the quadratics, of prefix 1 and average 2. The first had nested loop, and the second uses a slice, and that has O of j plus 1 again. The last uses j one time for everything. Okay, got you, Jeremy. Yeah, that's what kind of I was picking up on. Appreciate you clarifying that. Okay. Three-way set disjointness. Suppose we are given 3 sequences of number A, B, and C. We will assume that no individual sequence contains duplicates. Okay, hold on. Sorry. We are given 3 sequences of numbers A, B, and C, because these are all individual lists of arrays of numbers. We will assume that no individual sequence contains duplicate values. But there may be some numbers that are in 2 or 3 of the sequences. Okay, so each of these are tuples, right? Or is it tuple or set? I think it's tuples, right? They're tuples in the sense that they do not have duplicating values, but the values can duplicate varying list to list. Is it a tuple? In Python, a tuple is a built-in data type that uses to store and order immutable collection of terms. Tuples can contain elements of different types, and their immutability means that once created, they can always change. So these are just immutable. So maybe not tuples. They might be not lists, not tuples. Oh my gosh, what is that word? What is that word? Sets. A set is a built-in data type that represents an unordered collection of unique items. Okay. So these actually, these are not tuples. These are sets, from what I'm gathering, because they can be, hopefully they can be, iterated and changed the order of, but, okay, so they could be a tuple or a set, actually, so we'll see. In 2 or 3 of the sequences. The three-way set disjointness problem is to determine if the intersection of the 3 sequences is empty, namely, namely that there is no element x such that x is in A, x is in B, and x is in C. A simple Python function to determine this property, if given in code fragment 3, is given in code fragment 3.5. What's this is in, right? Is in an element of. Okay, belongs to. Yeah, so this is trying to identify if a value is inside all 3 of these data sets. Jeremy Fuller says Python is nice because there are functions built to allow you to do things like slice very easily, but you have to remember that there's code behind the Python standard library functions, and the code you don't see has a time complexity of its own. Exactly. So if I run the sum function, well, behind the scenes on the sum function, there is looping going on or whatever. So I have to take that looping over, some value range n. So um, I have to keep that in mind. All right. Bear with me, guys. We are almost to the practice problems at the end of chapter 3. Those will be a lot more, you know, interactive, and as the people that were here for the chapter 2 problems, they were a lot more fun. Definitely, the reading, we got it's critical to read and learn, but then we need to but we get to have the fun and apply afterwards. This is just kind of the monotonous part, but we'll get there. A simple Python function is given in this fragment. So disjoint ABC. So we're giving these three data sets. And so for value in A, for value in B, and then for value in C, if A is equal to B, B is equal to C, and B is equal to C, or A is equal to B and B is equal to C, and they're all equal to each other, return false, else return true. We found a common set. If we reach this set, disjoint one. Okay, so you're trying to determine are these sets unique, and so return true basically. If you detect a number, return false. Maybe the inverse of the function would have been like, do you detect a number, return true, but it's returning false if you detect a number. So but because it's disjoint. Algorithm disjoint 1 for testing three-way set disjointness, right? The simple algorithm loops through each possible triple of values from the three sets to see the three sets to see if those values are equivalent. If each of the original set has a size n, then the worst case running time of the function is n cubed. So we have a cubic function, right? So this simple algorithm loops through each possible triple of values. What is triple of values from the three sets? To see if they're equivalent. If each of the... Okay, yeah. Right, because we're just iterating n times here, we're iterating deeper n times one more level, and we're iterating deeper one more time, so we're we're going deeper n times n times n, and so we have n cubed time, O of n cubed, okay? We can improve upon the asymptotic performance with a simple observation. Once inside the body of the for loop over B, if selected elements A and B do not match each other, it's a waste of time to iterate through all the values of C. Exactly. So what if we can check here after B to see if A and B are correct? If they're not, then we don't even need to check if C is correct, because we already have the answer we're looking for, that that these are going to be disjoint for that value. Disjoint means they are not in all three of these, right? Or it's not, the value isn't in all three. So what they're going to do here is they're going to say for A and B, A, and for B, for value in B, if A is equal to B, then go ahead and look for C. If it's equal, then return the false that we found value, and then also return true, right? So the improved version is not simply in the improved version, it is not simple. What I cannot read tonight. Sorry, guys. It is not simply that we save time if we get lucky. We claim that the worst case running time for disjoint 2 is O of n squared, or it's a quadratic, right? There are quadratically many pairs A, B to consider. However, if A, B are each sets of distinct elements, there can be at most O of n such pairs with A equal to B. Therefore, the innermost loop over C executes at most n times. Interesting. Right, because we do, so what it's saying is we have a for loop out here then we have another nested for loop, and we do a condition check there. So at this point, this would have a quadratic time, but this section here would be in linear time, O of n time, because the management of the for loop over A requires O of n time, right? This is O of n time. The management over the for loop over B accounts for a total of O of n squared time. So O of n time, and then this one is O of n time, but together O of n squared because it's nested together. Since the loop is executed n different times. The test A is equal to B is evaluated O of n squared times, right? Associated inside of this with this. The rest of the time spent depends on how many matching AB pairs exist. As we have noted, there are at most n such pairs, and so the management of the loop over C and the commands within the body of that loop use at most n squared time. By our standard of the application, it's n squared, yeah. So right here where it says, however, if A and B are each sets of distinct elements, there can be at most n O of n such pairs with A equal to B. Let's get caught up on the chat. Alimi says the link is good now. Awesome, I appreciate it. Good, thanks for letting me know. Jeremy says, oh no, we already read that one. Ajax, thanks so much for leaving a comment and joining. I appreciate you joining. He says, wouldn't worst case it would be O n cubed? Oh, so it's O of n squared plus O of n. Yeah. So that's what it's saying here is that, right, at this point we're only evaluating if C is equal to, I'm trying to break this down to see at what point and why. I know it explains it here, but there's just a lot of jargon. So, however, if A and B are each sets of distinct elements, so if A has 0, 1, 2, 3, B has 4, 5, and 6. No, A has 1, 2, 3, B has 4, 5, and 6, sorry. Right? There can be at most O of n such pairs with A equal to B. Little a equal to B. This part I don't understand. However, there can be at most O of n such pairs with little a equal to little b, which is just the values. O of n such pairs. Ajax says, worst case it goes through all A and all B, so it's O of n squared, right? And then it just goes through C once, so it's O of n. Okay. Yes, I believe that's correct. Because at this point, you're only checking that singular value, right? And then you just iterate over through through the C, and you have O of n time and do that comparison, which is just a constant operation, a constant time. So yeah, I believe that's correct. That means every number in A and B are equal to O of n. Okay. Element uniqueness. Yeah, so this runs an O of n squared times a quadratic. Okay, a problem that is closely related to the three-way set disjointness problem is the element uniqueness problem. In the former, We are given three collections, and we presumed that there were no duplicates within a single collection. In the former, we were given three collections, and we presumed that there were no duplicates within, okay? In the element uniqueness problem, we were given a single sequence S with n elements and asked whether all elements of that collection are distinct from each other. This is like a leak code problem, I feel like. We're doing leak code problems, like the OG leak code problems built into the textbook. Oh, that's funny. We're just on chapter 3. We're getting hello, Martin. I appreciate you leaving a comment. He says, what structure are you learning right now? We're just learning about we're getting introduced. We were taught the 7 functions, introduced in this book, the constant, logarithmic, linear, n log n, quadratic, cubic, and exponential. We were then introduced into some asymptotic analysis with growth rates, with big O notation, big omega, and big theta. And so now we're just going and looking at some actual, algorithms and optimizing them, essentially, and evaluating their time conditions. Okay. Okay. So, got you. Our first solution to this problem uses a straightforward iterative algorithm. The unique one function, given in code fragment 3.7, solves the element uniqueness problem by looping through all distinct pairs of indices, j less than k, checking if any of those pairs refer to elements that are equivalent to each other. Sorry. Yeah, those pairs are equivalent to each other. It does this using 2 nested for loops. Okay, so let's look at this function first. So we're given a sequence S, right? And we're going to return true if there are no duplicates in the sequence. So if the sequence is in this case, is a set. So we first find the index. So we're going to find the index. We're going to save the index value as variable j. So using range length of s, we're saving every index value as length j. And then we say for k in the range of j plus 1 all the way to the length of s. So for k in the range of j plus 1, because we don't want j to be 0 because we're going to have an index value of 0, so j has to be j plus 1 in this position, and length s. So, but why are we iterating again through here? What are we doing exactly? Okay, so okay, I see. So we are finding the index value we're saving the index value of the length of the list for j. We are then looping through the now we're saving the value, so this is a value, I believe, for k in the range of oh no. So we're still actually getting another index value here. But instead of just to the length of s, we are saving another index value, 1 greater than j, all the way to the end of the list. So we are checking then if that index sequence at j is equal to the index value at sequence k, or at index k. And so, yeah, that's interesting. Avinash, I study for about an hour and a half to 2 to sometimes even 3 hours a day, and then I on the weekends I try to do 3 plus, maybe sometimes even up to 5. So j plus 1 is necessary, or we would be comparing the same elements. Exactly, right? If you were just doing to j all the way to the length of it, you'd be comparing the same elements. But j plus 1 is 1 greater than the current element you're on, so you're comparing the next element. Okay, so I'm gonna like let's do like a little dummy example here. So if we have an array is equal to let's say 1, or let's say like 2, 4, 6, 8, right? This is our array. It has index values of 0, 1, 2, and 3, right? So we're going to loop through and find it. We're going to save these index values as these are going to be j, right? And then for k in the range of j plus 1 to the length of s. So we have, let's go like this. Ooh. K is going to have j plus 1 to the length of s. So it's going to start here. Right? And so and then this check here, we're checking the sequence values at those individual indexes for each loop at those points. So we're gonna start off at this value right here, boom, at index 0, right? According to this one, according to here, right? Where we have index 0 is right here. Then we're going to save the next value of k. The first value that k in this loop is going to be saved as is index 1. So it's going to be accessing the 4. It's then going to evaluate s at index 0. Is it equal to s at index 1? Well, is 2 equal to 1 or 2 is equal to 4? No. So it's going to keep looping, right? It didn't get it. If it is, it didn't get this Boolean true, so it's gonna not return false but keep looping. It's then going to move on to the next number in j, which will be the 1 index value. So 4. We had j plus 1, so if j is now the 1, k is now 2 index, which is going to access the 6 value in our array. So on this one, we're going to evaluate, is 4 equal to 6? No. This Boolean returns false, so this does not does not compile, and so we go back into our list, go back into our loop. We then move on to the next value of j in the range of length s. That is value index 3. Or sorry, 2, my bad. We then move on to the next value of j plus 1 at the end of the length of the list. So if the current value of j is 2, or j plus 1, which is 3, which is k. So now we're going to evaluate if these two numbers are the same. Oh, this Boolean returned false, so we can't move on and actually return false. So we're going to then come here. Oh, we have no numbers left in our range length of s. We are at the end of our value of s. This is it. Because our range is 1 less than the length of s, we don't want to actually move on anymore because we can't access another k plus 1 value. So this is good that we didn't say length of s plus 1, or so it would try to move on. Just the length of s, because the range stops 1 short of the length in terms because it's 0 indexed, right, just by our inside knowledge or by programming knowledge. And so this is going to completely exit, and we're going to return true, meaning that this array is unique. Cool. So that was definitely very helpful to walk this through step by step and kind of actually write it out and see, okay, if we're at index value 0 for j, and well, if k is just j plus 1, starting there, so then we're at index value 1, so we're evaluating 2 and 4 at that for loop point, in this section. So very good, very cool. Hopefully that was helpful to walk through. It made sense to you guys. It made sense in my head, but sometimes I don't know if it really makes sense to other people, so let me know if that actually helped at all. Okay. So now let's try to determine the running time of this function without kind of moving forward. So we have a for loop here that iterates over our um, our sample value of our sequence. So we are automatically in O of n time here. We then have another loop, another nested for loop that also takes in the length of the sequence. So this will bring in O of n time as well. Wait, no, maybe, yeah, I think so. So together, this evaluation will be in O of n squared time, or quadratic um, upper bound in the worst case. Those pairs refer to the, okay, so it does, okay, so let's go back here. Our first solution to this problem uses a straightforward iterative algorithm. The unique one function, given in code fragment 3.7, solves the element uniqueness problem by looping through all distinct pairs of indices where j is less than k, because we are j plus 1 here. K is automatically one value higher than j, as we have seen in this kind of actual written example here for this loop. Checking if any of those pairs to the elements are equivalent to each other. It does this by using two nested for loops such that the first iteration of the loop causes n minus 1 iterations of the inner loop. The second iteration of the outer loop causes n minus 2 iterations of the inner loop, and so on. Thus, the worst case running time of the function is proportional to n minus 1 plus n minus 2 all the way to 2 plus 1. Which we recognize as the familiar O of n squared summation from proposition 3.3. All right. Jeremy says, checking the next element after J with K. Yes, gotcha. Copter, thanks so much for joining. I appreciate you coming in here. Long time no see. Jeremy says, so J plus 1 is necessary or be comparing the same elements. Gotcha, yeah. Chris Nevins, thanks so much for coming in. I appreciate you joining the stream and leaving a comment. Welcome. He says, geez, you must be doing advanced. No, this, don't feel daunted. I'm a beginner in learning this. I am just trying to push myself to learn something more advanced here. I've kind of been honing over and over again the same kind of beginner concepts. I did CS50P. I completed all of those problem sets and really studied that quite heavily, and then completed the final project and earned the certificate in that course. And then I also read aloud on stream and completed all of the in-text problems on stream for the Python Crash Course Part 1, which is the, again, the, instruction or, general knowledge of Python and how to use it and what it does. And the Part 2 is mainly just going into projects. But yeah, and then I'm also going back through and posting videos on my channel of the in-text problems, the try-it-yourself problems. I'm going through and posting those for other beginners like myself, but I've been teaching myself for about 6 months and doing this pretty seriously for about 3 or 4 now, since about September. I've been really kind of grinding away quite heavily, and then in the past month I've been doing these streams, ramping them up quite more often because I've just been really getting into it, and I like learning and keep stacking knowledge. It really helps to stack knowledge on top of one another because it just helps to kind of level up, and yeah, that's what we're doing. So don't feel daunting. We started in the shoes where we didn't know anything, and we slowly built up day after day, hour after hour, little by little. Just like it's not some YouTube guru kind of thing that I got a software engineering job in 2 months and I lived under a rock before that. It's like, no, this is not that case. So. Okay, gotcha. So using sorting as a problem-solving tool. An even better algorithm for the element uniqueness problem is based on using sorting as a problem-solving tool. In this case, by sorting the sequence of elements, we are guaranteed that any duplicate elements will be placed next to each other. Okay, so if you sort, right, if you sort the elements, you guarantee that if you have duplicates, they will come next to each other. So if you have a list that's out of order, right, let's say we have a 6 right here. If we sort this list, 6 and 8 will trade places, and just because of order of magnitude. And so then we can detect easily that the number k plus 1 or j plus 1 is is detected, right? So what it's going to do here is probably use that as a tool. So, but sorting in itself takes time complexity. As Jeremy mentioned before, they're going to use, I can already tell, they're going to use the sorted function in Python. And this in itself is probably going to have a time complexity of O of n squared, I bet. Um, maybe not O of n squared, maybe n log n or O of n squared. But I think it's going to be O of n squared for this sorted function. But that's just my guess going forward. Let's see if we're right. If we're not, oh well. Okay. So in this case, by sorting the sequence of elements, we are guaranteed that any duplicate elements will be placed next to each other. Thus, to determine if there are any duplicates, all we need to do is perform a simple pass over the sorted sequence. Looking for consecutive duplicates. A Python implementation of this algorithm is as follows. So we have unique2 function now, which takes in the sequence. And so we have a temp, which is a temporary variable, I'm guessing. And we save the sorted sequence of s as temp. So the sorted function returns a new, no, the sorted function doesn't return any list, right? And so you have to actually save the that list as a new variable. It just, no, sorted does return a new list, but dot sort, the method, sorts the original list, I believe, right? So the sorted function, when given an input value of s, returns a new list that is sorted s. And so we save that as temp. It doesn't override s, I believe. I believe the method dot sorted does. I could be wrong. Let's go like this. Let's check. Does the dot sort method override the current list? Yes, the dot sort method modifies the original list in place because you're applying a method to the instance, which is that list instance or array. It does not return a new list like the sorted function does. So that's the difference between the two. And so we can actually save that new list as temp variable, right? And then what we say is so what we do the same thing, we get an index value, but we don't start at 0, we start at 1. So we don't actually want to start at index 0 for j, because we want to actually just compare that first number right off the bat. We don't, or right with the second number. So if sequence of j minus 1, right? So because j is going to initially start at 1, we need to say the previous number 1 back from j is equal to the current index value of at sequence j, right? So for our purposes here, we have j, which is going to start at sequence 1 rather, right? It's going to start at index value 1, which is going to be applied to this 4. The 2 is going to be applied to the 6. The 3 is going to be applied to the 8. And the 5, or the 4 is going to be applied to the 6. Or let's go one less number. We need to get rid of this. So let's do a duplicate. We need a duplicate for this example, right? So 1, 2, 3, 4. So j now starts at the second element in our list and goes to the last element, right? The length of temp. If, right, we have this conditional here, if sequence, this point, so what sequence is this? This is j. Our first is j plus 1, j1, so j minus 1, so that's going to be 0. So this is going to be, I'll say, kind of new J, for lack of better words, is going to start off at 0 here, and it's going to compare J minus sequence J minus 1 is equal to sequence at J. So J is 1 index, so that's 4, and it's going to check 0. Is 2 and 4 equal to each other? No. So no duplicate pair, found duplicate pair, we return false. No, we're going to return, we're going to keep looping here. And then we're going to go one more over J. So now J is 2. Well, we need to find the value at S of J minus 1. So that's going to be, of this is 1 here. Right? And so now we're going to compare these two values, 6 and 4. No, we're going to do the same thing, right? We're going to move on to the J3. The next one becomes 2 that we're comparing. Oh, these ones are the same. We're going to return false. We found a duplicate pair. This set is not unique. They have duplicate elements inside. See, guys? We're getting it. We're getting it. We're doing it. We're getting it. Okay, here we go. This feels good. We have people in the chat agreeing here. Correct. Yep. Awesome. People are following along. All right. Cool. So the built-in function sorted as described in section 1.5.2 produces a copy of the original list with elements in sorted order. It guarantees a worst-case running time of O n log n. See chapter 12 for discussion on common sorting algorithms. Dang, there's 12 chapters? I did not know there were so many chapters in this book. Oh, this is going to be a grind, people. Well, follow along. We're in this together. Okay. It guarantees a worst-case running time of O n log n. See chapter 12 for discussion on common sorting algorithms. Once the data is sorted, the subsequent loop runs in O of n time, and so the entire sequence runs in O of n log n time. Hey, we were right. I said that was one of the two. We said it was either going to be O of n log n or quadratic. I just didn't know how the sorted function actually worked under the hood, but it looks like it's n log n. Gotcha. Cool. All right, guys, we're moving on 3.4 here. Wow. Okay, how close are we? So we're on 3.4, which is 137. And then 3.5 is exercise, 141. So we are 4 pages away from being done with the chapter here. Okay, I think that this is a good place to pause. I know I have been slacking heavily on the Small Business Manager project. So let's go ahead and get this loaded up. All right, you guys, this is the Small Business Manager. So we're going to shift focus here for maybe 30 minutes on the Small Business Manager. And yeah, just a little bit of time here. I'm going to watch a show with my girlfriend here. It is Friday night. I do want to enjoy a little bit of free time on Friday night. But tomorrow I will be back streaming bright and early. I will be streaming probably around maybe 10 or 11 o'clock up until maybe 2. And then continue streaming and then maybe do another night session after that. So we'll see. All right. Or I might even stream from like maybe 11 till like 5 or 6, or could be a pretty long stream, like 5+ hours. So tomorrow, a lot of stuff coming. So we're definitely going to finish chapter 3 tomorrow, get into those problems, and get some stuff done. Okay, so let's go ahead and give a demonstration of what's going on here, guys, for those that are new. So this is the Small Business Manager project that we've been working on in Python. We have a Git repo here set up. We have a git.dataignore, which just ignores our PyCache, which is just the compilation of our code and stuff like that. We have we're ignoring our virtual environments. I don't believe I have one set up right now, but we're just ignoring that for right now because I don't have any third-party packages installed, but we should probably initiate one just to be safe. And then we're also ignoring our CSV files because those get auto-created if they're not there. So Um, what we're doing is we have a this is a small business manager project where we are um, allowing the user to manage inventory items and then convert those inventory items into sales and then generating hopefully sales reports and maybe tax reports based on the business. So we have a class here, which just is an item class as a base class, which has just some basic parameters or attributes that the user can apply to them or will need to apply to them. Some of them have default overrides of none, where if they aren't provided, they get set to the current date, as if they were logged in today. We have a for sale item class, which is a child of our item class, which adds in a couple new attributes, such as the listing price and the date listed. And then we obviously super all the other ones from the in and above. We have a sold item class, which then converts the for sale item into a sold item. And due to that, we add in a sold date and a sold price as well, and super all the rest. So it's pretty simple. Um, so yeah, now what we're doing is if I go ahead and run this program, I have some creations of items happening here. Just I've inserted here um, to be dummy and just be a tester. So if I go ahead and run the program, we are prompted with, would you like to open the small business manager? And we'll say yes. I just have a print statement here happening from right here, just so I was seeing an accessible data point. But if you stay with me here, if I exit out of the program and say yes, you'll be able to see that all of our creations of these instances were successfully saved into the file after we exited the program, and they were successfully generated within those test blocks of code I have here. So all in all, that's working appropriately. So I'm going to go ahead and just delete um, these tester blocks here. We don't need them anymore. And we are going to move on to actually getting some more features added to this. Jeremy says, LOI, I remember when I first learned OOP in Python, I spent like an hour to realize I wrote single in it instead of dunder in it. I've actually done that too, where I've forgotten to actually put the dunders, or I usually actually forget to put def out front for some reason. So that's my problem. Okay, so I'm gonna move my terminal window over to the side of my screen here, exit. Okay, so let's just add in maybe one or two features here before we log off, little bit by little. I'm going to get a lot of work done on this weekend after we finish chapter 3. I've just been heavily focused on chapter 3 while everything's been fresh on my mind and solidifying these algorithm concepts because when we actually start sorting these items, we're going to want to use efficient sorting mechanisms because the user um, will have probably up to thousands of items in their inventory potentially, and we want those to be sorted by certain conditions and by certain filters. And so this is going to be directly implemented into these projects. So stay tuned for that. We are going to be putting these algorithms into our projects when we learn them, and actually putting our money where our mouth is here. So that's the whole purpose of this learning. It's all tying in here little by little. So we have a run inventory function which we need to actually establish. So below here are operational functions which just create kind of things or do certain functions, but we have our process functions above in this section which are like our flow for our script or our project here. So let's go ahead and establish a run inventory function so that we can create this inventory. So we're going to prompt the user with a why am I getting a oh yeah, it's because I have this open function. So we're going to create a menu here. We're going to give it a prompt of Um, so how would we like to display this inventory? That's the question. Do we want to have a menu prompt with like to view inventory? Maybe let's just get something on the board here. We can think about it all day, but let's get something actually written. So, um, inventory manager. Um, so this is the inventory manager screen, and we're going to give it a list of options of what's going to be our first option. View inventory. We're going to give it another option of let's do view. It's another option we can apply to this menu for inventory. What do we want to do? We can view. From there we can then sort, obviously, so we'll get that later. So what menu we have? Inventory, transactions, and exit. So transactions is where we'd be like to add items. No, so inventory is where we go to. So view. Let's do add item to inventory. Right? And then, so we can add item to inventory. We can remove item. So we can add item, remove item. We can so we can add item, we can remove item, and then we can edit item, right? We want to edit an item in case we need to override a parameter. Find item. So I'm gonna do find slash edit item together, and then we're gonna do view mode. View inventory. Right? So these are going to be our options here. So let's go ahead and run. So if you run this, we're into here. Would you like to run? Yes. Okay, now we get into this menu. Small Business Manager 1.0, version 1.0 by Michael Deming. Now if we go into inventory, we get the loop. So we need to actually add in. So now we get this. So we need to actually, in the run inventory, we need to say clear terminal here. So we actually get the clear after we get this input for the inventory manager screen. I want to, I'm going to put a, what happens if I put a new, that will, inventory manager. What if I do in the create menu, I need to add in a print prompt. with a \n here. I want the prompt to have one space before we get our menu items. And then I want to do prompt I have with the colon here. So now if I save this and clear out of here and then run my program, right, we get the spacing now. Do I like that? Let's check. So let's dive in. I like it there. I don't really like it elsewhere. Let's check in the inventory. I think it helps clean things up, definitely. What do you guys think? Okay. I think I'm gonna remove the colon and just have, because the first one didn't need a colon, my first prompt. So that definitely can be optional for the user to add. So then we want to say, okay, let's get back to it. Sorry, lost my train of thought there. Okay, so we're in our run inventory here. We have add item, remove item, find, edit item, view inventory. So if the user presses 1, right, we want to add an item, but so create a new item, okay. So if they press 1, we would need to add a new item. So let's just get this kind of structure set up before we start worrying. We don't need to worry about the actual intertwinings of the functions right now. We'll figure those out, but let's just get the, so if, so we need to actually do user input right here for the create menu, because it returns a value. If user input is equal to quote unquote 1, ooh, right? I've programmed in a couple days, you guys. I definitely need to, I gotta program every day after my learning. I get rusty for sure, quick. If user is equal to 1, we're going to run add item. Okay, we're gonna run add item function. Right, we'll just break it down like that. Elif user input is equal to quote 2. We're going to run the run remove item function. Elif user input is equal to quote unquote 3. We're going to run the run find edit item function, right? And then the elif the user input is equal to quote 4. We're going to run view inventory function, right? So if we are gonna, okay, and then we need to encompass all of this inside of the while loop. Okay, so we'll put this all in a while loop. So The user has to stay here um, before they can move on. If they don't provide one of the inputs we're looking for, we're going to continue the loop. Okay. Perfect. Okay, so Jeremy says, "Nice job. You picked CRUD, create, read, delete, update. Only issue is you can divide down the database rabbit hole now." What do you mean, Jeremy? CRUD. Oh, it's acronyms. Create, read, delete, update. Only issue is you can dive down the database rabbit hole now. What do you mean by that? All right, guys. If you guys have any like features or things you want to implement, or maybe some better ways of doing things, please feel free to chime in. Like, I want this to be interactive. I want you guys to participate. So don't feel like this is just strictly me and my ideas only. So, okay, so we have this menu now set up for the run inventory. We want to then, okay, so let's test this out now. We need a way to go back though. So we need to add in a back here. Main menu for, right? So we'll add a main menu option here, and then we'll need to add in another elif condition. The user input is equal to quote unquote 5. We want to, if they go to main menu, we want to run just, we want to call so this loads on the run system call. So we don't want to load items here. I'm going to take these bits of code. We don't want to run, because I'm going to call this run system again to get into this main menu, right? This is our main menu. So instead of, we don't want to redetect the items in the file. That'll just probably repopulate them and duplicate them if we have this here. So instead, I'm going to Command X and get rid of that here. And I'm going to put it, if the user decides to run system, instead of just running the system here and having them be inside, I'm going to put them here. That way they will be initially added into the system when they press 1, but not every time the run system gets called back for the main menu call. So that will take care of that. So now we can come back down here, and if they say exit 5 to go back to main menu, we can just call run system, and this will bring us back into our main loop here. So if I can go ahead and I can show you guys here example. So let's go ahead and run the program. So I can enter in here. Right there, right when I pressed 1 right there, right when I pressed enter, it would have read the files, not into this menu here, right? So now I can go to the inventory, and then I can press 5 to go back to main menu, and I can get back to the main menu here. So Jeremy says, how do you handle an input that is not one of the options in the menu now? Yeah, so in my my create menu file here, so in my create menu function, so I had to figure that part out. So what I did is I checked if the options they provided is an instance of a list or a tuple. So it has to be an iterable type in a list or a tuple, and it can't have list tuple. I probably could add set here. Right? I could add set here definitely. So a iterable object. Um, so it has to provide that. If it does, we'll go ahead and proceed. Else, we'll raise an error saying menu creation is unsuccessful. Please list tuple set. Um, okay. So while true, we're going to run a while loop, and we're going to um, display the prompt that the user provides. We're going to, enumerate over the options, saving the index value, and then, creating that menu here. We're going to ask for user input, and then we're also going to confirm that that user input is int. We have to confirm that it is int and in the range of the length of options +1. So this one was actually really fun. This function was one of my favorite functions to actually write. It was really fun to do on stream. We did it all together when we wrote it with a few others people, and it was really cool because we were able to, um, you know, it, it just all worked out really well, and it was just kind of seamless, and it just felt really good to write because we were able to, detect. We had to detect that that int value was in the range of the length of options +1, um, so it can be detected in as 1, 2, or 3 here. So it checks to make sure that they provide either 1, 2, or 3 for the menu options items that are listed in the options. Um, not attribute. Not what? Come on, forgot the word. Okay, so now what we can do is now, yeah, if I go to inventory, press 1 now, our main menu goes, and we're not going to be creating a bunch of objects at the same time, right? Now if I go back to my item class here, I kind of wish I saved somewhere those dummy creations so I could use them again, but um, yeah. Okay, so let's go ahead and so we have the run inventory system menu created, and we can obviously add some more options here, some more features that we want to do within the inventory. But then we need to add def run add item function. So this is going to be, I know guys, it's a lot of menus within menus, but without creating a GUI, it's kind of hard. I don't really know another way to really do this. I know I've looked at some other CLI programs and projects on GitHub, and they kind of just had the user provide commands into the actual terminal, like to do things like to create the objects. I think, what is that module called? What is that module called? Oh my gosh. Wait. Um, what is that module called? Not key input. No. No. It's not sys. No. What's that module called? argv. It is sys. It's sys.argv. Okay. So you can they've used sys.argv to get arguments from the CLI, but we're creating menus here. So it's just another way to do it. But I can tell you guys, I'm getting a little bit tired, so I might have to wrap it up here in the next. I was gonna try to stop by about 9:30. Um, Okay, but we will be back tomorrow bright and early. I'll probably be on around maybe 10, 11, or 12 and be streaming for about 5 or 6 hours. So it's going to be a big learning day tomorrow. We're going to finish chapter 3. We're going to start on some chapter 3 practice problems, really get some good practice with those algorithms, big O notation, all that stuff. And then it'll be, yeah, it's going to be a good day tomorrow. We're going to feel really productive. And I'm also going to work on, hopefully this weekend, publishing some CS50P solution videos to my problem sets and getting those on to the Discord private, publishing those private and getting them to the Discord members. Um, yeah. Okay. So we have run add item here. So in here we're going to clear terminal, right? We're going to create, we're going to have user input is equal to create menu. We're going to give it a prompt of um, we're going to give it a title of no, so run add item would be, so if we want to add an item, it would simply, we wouldn't actually need to, I don't want to create menu. I want to say um, item name is equal to input item description, item title. We'll just say item name. Right? We're gonna have the user provide an item name. We're actually going to, here we're going to print we're going to add new item to inventory. We're going to run item name, user input. I could probably actually remove this print call initially to make one less function. For user input, add new item to inventory. And then we'll say \n right here. I'm going to do 2 of them. Okay. And then we're going to say what other attributes do we need from the user? We need a name, cost. Oops, what happened? Why did that do that? Okay, so we need a name, we have a cost. Cost of good, right? Item, size. So we're gonna have the user input a bunch of We're going to do a series of questions. Item underscore number, it gets auto applied. So item number is going to be generate item number. So we need to have a function here for generating the item number for this item. So what this is going to do is going to this function, what it was going to do is we need to detect the next item in our available slot in our list. So if we have already have 5 items in our inventory with item numbers 1, 2, 3, 4, and 5, we need to detect that the next available position is item number 6. So we're going to do a function generate item number here to, I think the easiest way to do this would be to just actually access the use index -1 of our item list, current items list, all items dot items list, right? And assign the item number +1 of that last item in our list. So right, and then we'll need to ask for a date created. I'm going to create menu here. I'm going to say no, I'm going to do a function. I have an idea. So all I'm going to do is I'm going to have a menu. I'll maybe just do it right here really quick, and then I will just copy this into a function. So we'll create a menu. We will say generate, or what should we say if we want to use today's date or not. So by default, the user can provide none for date created to just automatically assign the current date as if they are adding that inventory acquired on that date. But if they acquired it in the past, they would need to obviously specify that. So date created would be, we would create a menu to ask the user for a menu, or for use today's date, right? Would we want to use today's date? And then we'll provide a list of options, right? Of yes, right, or no. So if the user selects yes for today's date, so this is actually going to return an input. So I need to say, I'm just going to copy this down here and go like this. So user input is equal to, we're going to create menu and use today's date, yes or no. If user input is equal to quote 1, we want to return none, right? Else elif user input is equal to quote 2, we want to we'll have to cross that bridge when we get there, because we'll need to add in a feature here for allow user to enter in custom date for past purchase, custom date in the past, right? It can't be in the future for a in a certain format, because right, the date time has to detect this format in order to create a delta element or date time element from it. So we need to allow the user to enter a custom date, right, if they press 2. So then what we're going to say is this will be sorry, it's user input. This will be while true user input, and then we're going to put this under the while loop. We're going to say else, oops, sorry, fat fingers, else continue with the loop, right? So right now we're just going to pass just to get rid of that error, but we need to add this in here. So we'll return break out of a while loop. Will return break out of a while loop. Yes, a return statement will exit not only a while loop but also the entire function or method. Okay. So we'll return none if they get 1 here, pass, else continue. So this will be generate date created function. So I'll take this entire function right here that I just wrote, Control X, come down here, def generate date created, and I'm going to pass it this. Okay. Okay, then so that we're gonna have a similar thing for generate item number. Okay, so then let's say for generate item number, what we're gonna want to do is right, so the item number is going to be the next available number in our list of numbers. So we need to first access the last item number is going to be equal to the all items dictionary dot with the items key dot item number, no, index, sorry, index -1 dot item number, right? So what this says is I'm going to access the all items variable. Well, the all items variable is a global variable above. So I actually need to all items can be found here. Okay. So the all items method here. So we go to that dictionary. We access the items key, which houses a list. The values for the items key is a list of all of the items. So we want to access the last item in that list, and then we want to generate item number, right? So what we want to do actually first though is we want to try and do this. Why do we want to try and do this? Because what if there isn't item in the list except for a value error or zero index error? What error do you get for a index that does not exist? When you try to access an index that's not an index, you get an index error. Okay, so index error. So if index error, except for index error, we want to except if we get an index error, we can't access this because there's currently no items in the list. We want to return what do we want to return? We want to return one, right? This will be the first item in the list. Yes, so all items is a dictionary where you have key values, items, for sale items, and sold items, and then we run load file on with the tag type items. We run load file with the tag type for sale items, and we run load file for the tag type sold items. And what this does is it returns a list of all the found detected for sale items, sold items, yada yada yada, already detected in our program. Right? And so then okay, so generate date created, we have, or sorry, so except if you get an index error, meaning that you can't access this item, so try access this item, and then we want to we want to assign return. We want to return last item number plus 1, right? So this will generate the next item number if there is an item in the list. Except if we get an index error, meaning that the list is empty. So we could technically say we could technically like do a bool like if rather than the end. What do you guys think? Would it be better to do a bool statement at the front, like, and say if all items, key items, right? This will just directly tell us if there are any. Go ahead and do this. Right? But this is, I feel like this is monotonous. This does essentially the same thing, right? These two lines of code do essentially the same thing. This try except statement. So if all items what do you guys think? Jeremy, what do you think? Right? So if all items, right, this will, if we have detectable items, then we can go ahead and try, we can do this. We wouldn't even need to say a try here, really. And we wouldn't even need an except statement here. We would just need an else statement to say, else that list is empty, right? And we need to just return one. Right? Let me see here. Let me go back. Oh, let me go back here. Like this. All right, here we go. Is there any difference? True. Is there a which is the better way? This way or okay, let's look at that. Okay, so let's ask the almighty orb here which one it likes better. Both approaches handle the situation effectively, but each has its pros and cons depending on the context. Here's a breakdown of one might be considered, quote, better than the other. First approach, explicit check with if. If all items, last item number, like return 1. Explicit and clear. The logic is easy to read and understand because it directly checks if all items is not empty. No exceptions raised. Avoiding exceptions like index error improves performance in cases where exceptions would frequently occur. Predictable behavior. It does not rely on handling errors to dictate the flow of the program. Additional disadvantages. Additional checks. If all items is large, checking if its truth value might add a small overhead, though this is typically negligible. Verbosity, slightly more verbose than the second approach. Second approach, try except block. Advantages, concise. This code is shorter than since you've only focused on the intended operation and handle the error if it arises. Pythonic in spirit. Python's philosophy also often emphasizes it's easier to ask for forgiveness than permission. This approach aligns with the principle by assuming all items has an element and handling the exception otherwise. Efficient for rare exceptions. If index error is an edge case, all items is empty or only occasionally. This approach avoids unnecessary checks most of the time. Disadvantages. Performance cost of expectations. If the list is frequently empty, raising and checking exceptions could slow down the program. Less explicit. Which is better? Use the first approach if you want clarity. Use the second approach if you want conciseness. And the list is to be expected not empty most of the time, making index error a rare occurrence. Yeah. So I think I'm going to go with the first approach. Because I can't see all the code, I'm having trouble recognizing why the list would be empty if returning 1 would work. So the whole point of this project, right, this what we're doing here is we're just trying to say right, we're just trying to detect if there are items in the list currently, right, meaning that there are already items in the inventory. Now if there are, we need to access the last item in that items list because we're creating a new item, right, and we need to access that item's item number because that is an integer. We need to then take that item number and add 1 to it and return that value and assign that to the new item we're creating item number. Use right here we're assigning this. We're generate item number is returning an item, the item last item number plus 1 as the new item number for this new item that we're creating. And so right, except if you get an index error, right, meaning that this list is empty. If you access this list and then the negative first index means the last item or the first item in this case, they would both resemble the same thing if the list only has 1 item. you would get an index error if this list is empty. So we would return a value of 1 indicating that this is the first item in the list, like the first occurrence of an item ever being generated. So I think this is pretty, and the almighty orb, oh, the almighty orb, said it was Pythonic, so we are good. All right, you guys. This is gonna be it for me today. It's getting kind of late. I'm not. It's Friday night, but I'm gonna bow out and watch a show with my girlfriend and hang out with her for a little bit on this Friday evening. And I appreciate you guys joining me today. Jeremy says, "Do you have an item class?" Yes, I do have an item class. So these classes are what I've been pulling all of the. I've been creating these um, instances of, and I'm filtering, or I have that load file that detects the type of kind of like has its own is instant check built in within it for loading items in the for sale item category, or the item category, or the sold item category, right? So it does all that. So I think this was pretty good. We added a good chunk of code here to our project. Little by little, every day we're gonna keep adding on feature after feature, and then after a month, we have a whole working project. So it's just you got to just keep grinding a little bit by little bit. It's not all in one day. Don't get ahead of yourself. Don't get defeated that you're not building Facebook in one day. It's not like that at all. It's social media likes to skew things a lot. But I appreciate you guys joining me today. This was a very successful stream. I appreciate you guys taking your Friday evening and joining me. I will be back tomorrow for a long stream on the weekends, probably upwards of 4 to 6 hours tomorrow. And we'll be studying all day, and we will get a lot of work done on the project, as well as finish up chapter 3 of data structures and algorithms in Python, where we're currently talking about big O notation and introduced to the 7 functions for algorithms that we'll be talking about in the book. And so, yeah, we'll be getting some practice with the end of chapter 3 practice problems, and actually getting to our hands on with those notations and things. So tomorrow's going to be a big day. So super excited for that. I'll see you guys tomorrow. Thanks so much for the stream, and thank you so much for 250 subs. Woo, making our way up. So it's really exciting, and I'll see you guys tomorrow. Join the Discord, also linked below, if you want access to a compilation of all of my study resources, from Python Crash Course to Fluent Python to Python Machine Learning to the data structures and algorithm, CS50P, all that stuff. And I'll be adding more features and more study resources as I do